Chapter 8, Section 9, Variation. This is the last section of Chapter 8. Now, there are 4 different kinds of variation models in our textbook. Direct variation is the first, and then inverse variation, joint variation, and then combined variation. For the most part, I'll be sticking with, or this lesson will cover, direct variation and inverse variation. All right, for direct variation, this is what I call the model equation. And I think it's important for us to understand what this equation says in words. But before I say in words what this model equation represents, you must understand that direct variation and all the other variation models put x and y in a relationship. So there's a special relationship happening between x and y that I will explain in just a second. Although x and y are in a relationship, k is considered your constant, so it's like a fixed value. So in words, this model equation says that y varies directly as x, or said another way, y is directly proportional to x. So really what that means is if x increases, y will also increase. If x decreases, y will also decrease. And there are a lot of real world applications for that kind of relationship. For example, if you're an hourly employee, the more hours you work, the more the more money you will earn. The less hours you work, the less money you will earn, right? So as one value increases, the other value increases. If one value decreases, the other one decreases. And that's exactly what's happening with x and y here. Now, k is called your constant of proportionality or constant of variation, meaning it's not changing, okay? The main thing I want you to take away from this is the direct variation model is y equals k times x. You will have to remember that, okay? All right, let's jump into a problem. All right, check out this first example. When exchanging currencies, the number of British pounds received is directly proportional to the number of US dollars to be exchanged. If $800 converts to 392 pounds, how many pounds will be received if $1,500 is exchanged? All right, the first thing you're going to want to do is figure out what kind of variation we're speaking about here. Now, the problem will always tell you. Right here, it says that the number, British pounds, so pounds is directly proportional to dollars. Pounds is directly proportional to dollars. I want you to underline directly proportional because that's what tells you that your model equation is y equals k times x. Whenever you have direct variation going on, then this is your model equation. So that's like step number 1, if you will, set up your model equation. Now, this statement here, the model says y is directly proportional to x. Y is directly proportional to x. We have, in this problem, pounds is directly proportional to dollars. Pounds is directly proportional to dollars. So instead of writing it with variables y and x, instead of writing it as y is directly proportional to x, we have pounds is directly proportional to dollars. That is to say, y represents pounds, and all this stays the same. And then x here in this model equation represents dollars, okay? Let me read that again. Pounds is directly proportional to dollars. Pounds is directly proportional to dollars. So instead of y and x, I like p and d just because it reminds me of what we're talking about in this problem, okay? So let me rewrite it. I don't like all these colors. All right, so a little less colorful there, okay? But I just wanted you to realize that pounds is directly proportional to dollars. Now, let us plug in the first pieces of information. Right here it says $800 converts to 392 pounds. Let's plug those values in. Obviously, 800 goes in for dollars because of the dollar sign here. So 800 in for D. And then 392 pounds, that goes in for P, 392. So I think that's the beauty of using P and D as opposed to Y and X. I'm not going to get confused as to which number gets plugged in for which variable. All right. So I'm going to insert or substitute my first pieces of information, and then I am going to solve for K. I'll solve for K here by dividing both sides by 800, and that will give me K is equal to 392 over 800. You need to simplify this fraction by dividing the numerator and the denominator by the greatest common factor, which in this case you can find it is 8. So I'm going to divide the numerator by 8. I'm going to divide the denominator by 8. So when I simplify the constant is 49 over 100. All right, so now that I know what my constant is, the next thing I'll do is I'll update my model. Okay, I'll update my model. Let me move this up. Well, let me move it about right there. So let me update my model. My model was right here, right? And now I know what P is. So now P is equal to 49 hundredths times D. Do you see that? I replace K with what it is. Now, the last thing you need to do is use the last piece of information. How many pounds, stop right there. You're looking for P. P is your variable. How many pounds will be received if 1,500 is exchanged? So $1,500. So 1,500 goes in for D. So let's do that. So P is equal to, the number of pounds will be, and then plug in 1,500 here. Let me move this down just a little bit here. There we go. And I like to kind of kill the zeros, so 2 zeros for those 2 zeros. So it's really just 49 times 15, which is 735. So P is 735. So that's your final answer. Don't forget about units, okay? So it's not dollars, it's pounds. I'd like to kind of recap this the process, because no matter what kind of variation model you're in, the process is the same. So if you'll allow me to walk you through the process again, the first thing is set up your model equation. And this step here was optional. I didn't like y and x because then I'm not going to know what number goes in for what variable. So I put p and d. But either way, the step number one is set up your model equation. Step two, substitute in the initial pieces of information and solve for k. Update your model would be like step three. And then insert the last piece of information and answer the question. All right, I thought you might appreciate these steps for solving a variation problem. Set up the model equation, substitute initial information, then solve for k. Update the model equation with your new k value that you just found in step 3. And then substitute the last pieces of information and then solve the problem or answer the question. Okay? All right, the next kind of variation we're going to discuss is inverse variation. Now, when you hear the word inverse, think opposite, okay? So instead of the model equation being y equals k times x, it's y equals k divided by x, or y equals k over x. Now, here is what this model equation is saying in words, that y is inversely proportional to x, or y varies inversely as x. So this kind of relationship, everybody, is the following. If x increases, y will decrease. Or if x decreases, y will increase. For example, maybe a real life example. Let's see. The more units you take in college, the less free time you will have, right? I think you could probably relate to that. Let's see. Here's an example involving construction, okay? So the more workers you have on site for the job, the more workers, the less time it'll take to complete the job, as long as everybody's working, right? So the more workers, the less time it takes to complete the job. Or I could say it differently, the less workers, the less number of workers, more time to complete the job. So those are examples of inverse relationships, okay? All right, let's get into it. Let's follow the same. Oh, by the way, K is still your constant, okay? It's not changing. Let's follow those steps that I laid out earlier to solve the following application. All right, check this out. The intensity, I, of light received from a light source varies inversely as the square of the distance from the light source. If a photographer 16 feet away from his subject has a light meter reading of, that should be the word of, let me fix that for us, has a light meter reading of 4 foot candles of luminance, what will the meter read if the photographer moves in for a close-up 2 feet away from the subject? Now, I don't know how you feel, but this problem seems overwhelming to me. It seems long, and I don't really understand what it's saying. So first things first, okay, let's take it sentence by sentence, sometimes even phrase by phrase, and follow those steps I laid out earlier. Number one, let us figure out, let's start from the very beginning, start reading from the beginning, and figure out what kind of variation we're talking about here. The intensity, I, of light received from a light source varies inversely. There it is. Can we go ahead and highlight that, please? Varies inversely. That tells me right away that the type of variation we're dealing with here is inverse variation. So our model equation is y equals k over x. Now, the problem does not say y varies inversely as x. It says intensity varies inversely as the square of the distance. So instead of y varying inversely as x, we have intensity varying inversely as the square of the distance. So instead of using the letters y and x, I'm going to use intensity varies inversely as the square of the distance. So this is my model, ladies and gentlemen. This is what I call my model equation, all right? The only reason why the distance is being squared is because they said to square it in the problem. If they had not said the square of the distance, then I would not be squaring it. So just read the problem very carefully. All right, we got the model equation from the first sentence, okay? Now we're ready for the second sentence. And what we're going to do next is substitute the initial given information. If a photographer 16 feet away, stop right there, 16 feet away, is that intensity of light or is that distance? You're right, that's distance. So we're going to plug 16 in for D, has a light meter reading of 4 foot candles of luminance. 4, is that distance or is that intensity of light? That's intensity of light because it says 4 foot candles of luminance, how bright the light is. So let's substitute those pieces of information into the problem. Let's see if I can move up just a little bit here. I think that's good. All right, so intensity, I have 4 for intensity of light is equal to k over 16 squared. Don't forget that the distance is being squared according to the model equation, right? So let's come over here, guys. So you have 4. I can maybe move this back down if you'd like. 4 is equal to k over, and 16 squared is 256. If you multiply both sides by 256, you will get k is equal to 4 times 256, right? If you multiply both sides by 256. So that means k is equal to 1,024. Yeah, I know that because 25 times 4 is going to be, I know that 4 quarters is $1. So that's going to give me 1,000 because 25 right here represents 250, right? Because this 2 is in the hundreds place. So 1,000 so far, and then 4 times 6 is 24. Okay, everybody, watch this. I used the number 16 already, and I used the number 4 already. And that was given information, and I used it to find K. Now that I know what K is, I'm going to update my model, okay? I'm going to update my model. My model is right here on the screen. This is my model. I'm going to use my new K value, all right? So I'm over here. So I, intensity of light, varies inversely as, now this is 1024 over d squared, okay? Now let me go back to the problem, take the last piece of information, which is, what will the meter read? Stop right there. That means they're looking for intensity of light. What will the meter read if the photographer moves in for a close-up 2 feet away from the subject? The number 2 goes in for distance. (1024) divided by 2 squared, right? In other words, it is 1024 divided by 4, which will give you 256. Now, let's answer the following question. Let's answer this question using units, correct units. So the correct answer is 256 foot candles. I'm not a photographer, so I'm not super sure what foot candles mean, but that's the unit that the problem gives us, 256 foot candles. All right, I just want to mention this about combined variation. I did say that I would stick to direct and inverse, but I can't help myself. Combined variation has, it's an application that has direct variation and inverse variation in the same problem. For example, all right, the time it takes to build a highway varies directly as the length of the road and inversely as the number of workers. If it takes 100 workers 4 weeks to build 2 miles of highway, how long will it take? 60 workers to build 6 miles of highway? All right, very good. So notice that this problem involves both direct, right there, and inverse variation all at the same time. So let's see if you and I can build the correct model equation. It says the time, I need a variable for time. How about t? Time, or t, varies directly as the length of the road. I need a letter for length. How about L? It's like a cursive L. And inversely as the number of workers. How about W for workers? I'm just going to write right over it, okay? W for workers. That's a W right there. All right, so T varies directly as L and inversely as W. So I would love it if you pause this video and try to write the model equation on your own. All right, so time varies directly as the length of the road and inversely as the number of workers. So this is our model equation, everybody. Now this makes logical sense, right, everybody? Common sense to us, because the fact that time varies directly as the length of the road makes common sense for us. In other words, if the length of the road is great, right? If they have to build this long road, many miles, it's going to take them a long time to do it. But if the length of the road is very short, it's going to take them a short time, right, to finish the job. Whereas the time it takes varies inversely as the number of workers. And that was my example earlier. The more workers, the less time. The less workers, the more time, right? So all of that first sentence makes a lot of sense to us. All right, everybody, let's substitute the first pieces of information. Here we go. It takes 100 workers, so 100 goes in for W. All right, so let's do all of this. So 100 goes in for W. If it takes 100 workers, 4 weeks, so 4 goes in for time. to build 2 miles of highway. So 2 goes in for the length of the road. So we just finished using this number, and that number. All right. What we need to do right now is solve for your constant. Solve for k. All right. So this gives us 4 is equal to k over 50, right? Because 2 goes into 150 times. Multiplies both sides by 50, and you get that k is equal to 4 times 50, which is 200. Now that we know what k is, we can update our model equation to read like this. Time is equal to 200 times L over W. Now that we've updated the model, the last piece is to substitute in the last pieces of information. How long will it take 60 workers? So let's plug in 60. First of all, hold on. How long will it take? How long? That means you're looking for t. T is your unknown. And we just read that there are 60 workers, right? 60 workers to build 6 miles of highway. So I'll put 6 in for L. All right, so simplify this and work smart, everybody. And I don't think you need a calculator at all. I mean, after all, let's see, this 0 kills with that 0, or cross cancels. It's better than the word kills, right? So that pair of zeros cancel out, and then 6 and 6 divide out, so you're just left with 20. Actually, no arithmetic at all. So then t is equal to 20. 20 what, though? How is time measured? Weeks, right? If you read the question carefully, time in this example is in weeks. It'll take 20 weeks. All right, everybody, I hope you like this section. We covered direct, inverse, and combined variation. Awesome. This finishes chapter 8 entirely for us. So good job. Congratulations. We finished one chapter and we got a few more to go. So I'll catch you in chapter 9.